Hi, I'm Matt, and in this video we're going to introduce the concept of a limit in mathematics. More specifically, we're going to be looking at what a limit is and how we could see what the limit is based on a graph. So, what is a limit in mathematics? Often in math, we want to know as x approaches a certain value, what the graph is doing or what it's trending towards. More specifically, so as x approaches a value such as x approaches a, what the f of x value approaches as well. We write this with the following notation. So for example, if we were looking for the limit of f of x as x approaches a, if we denote the limit to be L, the notation is at what we have here. So we see that below the limit symbol, we have what x is approaching. So here x approaches a. And then here is where we put the function we're looking at. So here this reads the limit as x approaches a of f of x is equal to L. So now for an example, let's take f of x is equal to x plus 1. As x gets very close to 5, we'll notice that f of x gets very close to 6. So we would write this as the limit as x approaches 5 of x plus 1 is equal to 6. You'll see here we just plugged in 5 for a and x plus 1 for f of x and then evaluated it. However, and here we see that the limit as x approaches 5 and f of 5 are the same thing. However, this is not necessarily true. It is not always true that the limit as x approaches a of f of x is equal to f of a. Again, this is not always true, because the limit represents the value that is being approached and not the actual value. So let's look at an example of this. Let's take the function f of x is equal to the absolute value of x when x is greater than 0 or less than 0, but then f of x equals 5 when x equals 0. We see the graph as follows. Now I apologize, I know it's a little small, but you can see this is an open circle down here at x equals 0. So if we were asked the question, what is f of 0? Based on how our function is defined, f of 0 we know to be 5. However, the limit here is not 5, because from the left side, as we get close to 0, so as we look down this arrow and look down this arrow, we see that we're approaching 0. So the limit as x approaches 0 of f of x is 0. So again, here we see that f of 0 and the limit as we approach 0 are not the same thing. Next, it should be said that it's not even necessary to define what f of a is. So for example, going back to our previous example, we could now remove the definition of f of 0 equals 5 and just have f of x is equal to the absolute value of x for x is greater than or less than 0. So again, if we're now asked what f of 0 is, we would say it is not defined. Again, because we have that open circle down here. If we're asked what the limit is, we would again look down the left arrow and look down the right arrow, and we would see that we are still approaching 0, so the limit as x approaches 0 is 0. So here, even though we didn't define what f of a was or f of 0 was, the value of the limit did not change. Now, the last note about limits I want to make here is that for the limit to exist, the limit as we look up from the left and the limit as we look from the right have to be the same. In other words, f of x must trend towards the same value from both sides. So if we look at this graph here, we see that from the left side of point A and the right side of point A, on both sides, we're trending towards 0. So we'll say the limit as x approaches a, I call the function here g of x, we say that it exists. I'm not even going for what the value is here. So we'll just say that it exists for now. However, for point B, or as x approaches B, we see on the left side it approaches whatever this value is up here, while on the right side it's approaching this value down here. These are not the same, so we say that the limit as x approaches b of g of x does not exist. I'm going to put D and E from here and going forward. So now, how do we actually determine a limit from a graph? I know I've kind of alluded to this in my previous examples, but now we're going to formalize it a bit more. So the first thing we're going to ask ourselves is, does the limit exist? Or in other words, does f of x approach the same value on both sides of the x value of interest? That's just a fancy way of saying if we're looking as x approaches a, does the value of f of x trend to the same thing on both sides of a? The other thing we're going to ask then is, if it does exist, what value is it approaching? That's really it. It's just asking ourselves these two questions. Note that it does not matter if f of x is defined or if f of x equals the limit as x approaches a. So again, we're not going to ask ourselves what the actual value of f of x is. So now let's do some examples. So taking this graph here, evaluate the following limits. So first we're going to ask ourselves what the limit is as x approaches a. So we see that we're going to be looking at here, at this region here. So from the left side, from the left of a, we see that we're approaching 1. Similarly, from the right side of a, we're also approaching 1. Since we're approaching 1 from both sides, we could say that the limit of x approaches a of f of x is equal to 1. Point B is a little bit more complicated. We see that we have arrows continually going up on both sides of B. So what this is showing here is that on both sides of B, the graph of f of x is tending towards infinity. So that means that the limit as x approaches B is infinite. We'll say it's infinity. Similarly, if these two lines were pointing down, it would then be negative infinity. But again, that's not the case here. Lastly, for point C, we would say that the limit is 2, because from the left side and from the right side, the value of f of x is approaching 2. So again, we'll say that limit is 2. Note that even though the value is not 2, we do not care, because again, we are just looking at what it is approaching. Let's try another example. So for this next example, you'll notice that instead of supplying letters, we're now going to look for it where you're given the actual x value we have to look at. So the first thing we're going to look at is the limit as x approaches negative 6. That would be 1, 2, 3, 4, 5, 6. So we're looking here. We'll notice that there's a jump discontinuity here, and that's always going to be a problem for us when we're evaluating limits, because on the left side of the jump, you'll see that we're approaching positive 3, while on the right side, we'll see that we're approaching positive 1. So the limit from the left doesn't equal the limit from the right, therefore the limit's going to not exist here. And again, that's always going to be true when we have a jump discontinuity, that the limit will not exist. So again, the limit does not exist here. For x equals negative 1, we're now going to just look here, so we're going to be looking in this region. We see from the left that we're approaching positive 6, and from the right that we're also approaching positive 6. We could see that just by counting the boxes as we did for the x-axis. So we find that the limit as x approaches negative 1 would be positive 6. Lastly, we're going to look at the limit as x approaches 7, which we would count the boxes to find that is this region here, particularly along this line. So we see that from the left, we're approaching positive 7, and from the right, we're also approaching positive 7. Therefore, the limit as x approaches 7 is 7. Now, note that it didn't even matter that we had this point here, because again, it doesn't matter what the value of f of 7 is, it only matters what the value of f of x is approaching. So now, here's some extra practice. This is one more graph I've drawn up. I encourage you to try this on your own, and the answers will appear in 5 seconds. Okay, so the answer to this is that as x approaches a, the limit is 1. The limit does not exist at x equals b. The limit as x approaches c is 4, and the limit as x approaches d is 2. That's all I had for this video. Thank you so much for watching.